university is dealing with things, but so far I haven't had any, any problems or anything like that. I would say the conditions are not really ideal.
Yeah, right. I guess there are lots of suggestions about how one should be, with a mask and all that. And there must be many such constraints.
No? Not as many constraints as some would like. I would say, yeah, it's a complicated issue, but yeah, it's a very this is a very political issue in the United States and in general.
Yeah, I know this is indeed,
and in Georgia in particular. So people have really kind of chosen up sides about it, which does not seem to be the best way to respond to a public health issue. But anyway.
Yes, indeed. Good. So I think we are almost there.
Oh, hi, John.
You are giving 2 talks, one after another, and each of the talks is about 1 hour?
That is my understanding, yes.
With a half an hour break, is it not?
Yeah.
Okay.
Good. So no, I think half an hour break is good so that everyone can kind of take some mental rest and maybe have some tea and take a small rest. So Devendra, shall I?
Yes, sir. Start.
All right. So it's my pleasure to introduce Peter Clark from Georgia University, who is the speaker today for both the lectures. One now at 5:30, and then the other one will start at 7 o'clock. He will speak on the title for both the lectures is Triangular Modular Curves. So thank you, Peter, for agreeing to speak, and please go ahead and give your lecture.
Okay, thank you, Dipendra. Thanks for the invitation. Thanks to everyone for coming. I'm sure we're at a bunch of different times. For me, this is quite early, but I'm happy to be here. So I want to speak on joint work, with John Voight, who's here. So that's great. Maybe he can help out if need be. And so the paper was published a few years ago now. We worked on it off and on for quite a long time. So the specific work with John is the subject of my second talk. And so for my first talk, I want to give more general background and motivation. Okay, so let me share the screen now, okay, so you can see the high-tech setup here. Okay, so right, let me begin by speaking about a very specific family of branched covers of Riemann surfaces. So for an odd prime number p, I'm interested in the modular curve x of p, which is parameterizing elliptic curves together with a full level p structure, so full p torsion. And so because this is a moduli space of elliptic curves together with the p torsion structure, if you just forget about the torsion and retain only the elliptic curve, then you get a map down to x of 1, which is the moduli space of all elliptic curves, which is just the affine line together with the point at infinity, so it's the projective line. So this is the sort of map that I'm very interested in my first lecture, because this is a branched cover of Riemann surfaces. So in this talk, I'll use my Riemann surfaces will always be compact and connected, and I will use that synonymously with algebraic curve. If I don't say otherwise by an algebraic curve, I will mean a nice algebraic curve over the complex numbers. And then if I want to say something about defining it over a smaller field, then I will. Okay, so this is a Galois covering map. Okay, so in particular, there's a corresponding extension of function fields over the complex numbers, and that is literally a Galois extension of fields, or the group of deck transformations acts transitively on the fibers, the usual topological definition of a Galois covering. And the bottom curve happens to be the projective line. And the ramification is very limited and specific. It's ramified precisely over 3 points on the projective line. It's ramified over the special J invariants 17, 28, and 0, which will come in later in this talk. And it's ramified over infinity. The preimage of infinity corresponds to the cusps. And we know the ramification indices. In order, the ramification indices are 2, 3, and p. Okay, so if I want to view this over the complex numbers, then I have a very nice complex analytic picture. I have gamma 1, my modular group, which is SL2Z mod plus minus 1, that's PSL2Z. And then inside I have this, what's called this principal congruent subgroup of level P, which up to the plus minus 1 is literally just the matrices that are congruent to 1 modulo P. And so all of these things are Fuchsian groups. They're discrete subgroups acting on the compactified, if need be, upper half plane. And so I just have this map from, if you have a orbit under a smaller group mapping to the orbit under a larger group, then you get a finite map. And that's how you look at this map over the complex numbers. And so again, that gives the complex analytic picture, but there is also an arithmetic picture. This map can be defined as a Galois cover. So in this talk, when I say defined as a Galois cover, I mean the map can be defined, and the map is a Galois extension of function fields over that field of definition. Okay, so the cover can be defined as a Galois cover, not quite over Q. It can be defined over a certain quadratic field, Q adjoins square root P star. P star is either plus P or minus P, depending upon whether P is 1 mod 4 or 3 mod 4. That is the correct choice to make it the unique quadratic subfield of the P cyclotomic field that you get by adjoining a P root of unity. Okay, so this is kind of the example that I would like to generalize. This is sort of clearly a very interesting family of curves. It's a covering which has very interesting behavior. Okay, and so if you want some motivation for why this is already interesting, the Hilbert irreducibility theorem kicks in at this point and tells you that, so whenever you have this nice Galois cover, where the thing at the bottom is the projective line, it doesn't have to be branched over 3 points. If you have any Galois cover over the projective line, then Hilbert irreducibility tells you that the Galois group occurs over whatever field of definition of that Galois cover you have. And so you get from this that PSL2FP occurs as a Galois group over this quadratic field. That's a pretty nice result. Various modifications of this construction got PSL2FP as a Galois group over Q for certain congruence conditions on P. I had a paper where I did something like that, maybe around 2010. And then in 2015, I should say that a very nice paper of David Zawina showed that PSL2FP occurs as a Galois group over the rational numbers for all primes P via a different method involving elliptic surfaces. Nevertheless, it is definitely an interesting fact that it's interesting and non-trivial that PSL2FP occurs as a Galois group over this quadratic field, and that gives you a reason to be interested in these types of Galois covers of the projective line and trying to find their fields of definition as a Galois cover. And if we're interested in that, we should probably be more interested if that's so PSL2, again, this is a finite simple group as long as P is, rather PSL2FQ is a finite simple group as long as Q is at least 5, apart from the cyclic groups of prime order. Then you have the alternating groups, and then this is like the third family of finite simple groups. And it is already not known for most composite Q whether PSL2FQ occurs as a Galois group over Q. So it is interesting to study PSL2FQ branched covers of PSL2FQ Galois branched covers of the projective line for instance, because of this application to the inverse Galois problem, maybe that's kind of your foothold, and then maybe once you get in, you see that that's interesting for its own sake.
Is it possible to make the nodes larger, look larger right now?
Yeah, I can make it larger.
Yeah.
You want it larger? Hold on a sec. Let me see. Give me just a second. Should be able to make. Okay. Okay, now it's bigger. All right. So, right. So in these two talks, I would like to describe a certain generalization of this particular family. So in the first talk, actually, I'm going to talk about a wider generalization, but say less about it. So I would like to talk about the class of Riemann surfaces that admit a Galois-Bailey map to the projective line. So I'll define what I mean. And then in the second talk, I would like to specialize to the case where the Galois group is either PSL2 or PGL2 over a finite field. This is the work with John Voight. And so again, there'll be the features of this first example will be generalized as well. These will be uniformized by explicit congruent subgroups, and there will be information on the fields of definition as a Galois problem. Okay, so that's where I'm going for both talks. So yeah, so let me begin. And so again, I'm pretty sure that I will touch on material that has been covered in previous talks. I didn't watch all of the previous talks, but I watched parts of them. And I think that's good if I'm covering material that's been mentioned before. So if I cover it rather quickly and in my own way, then it's great if you have some prior familiarity. So I want to begin from a very kind of naive perspective, or at least elementary perspective. So I'm going to have three integers a, b, and c. They're each greater than or equal to 2. I can assume that they occur in increasing order. And so first of all, what I would like to define is just a group by generators and relations. So my triangle group, delta bar of a, b, and c, you won't find out until towards the end of the second lecture what the bar is doing here. Eventually there will be a group without the bar. Anyway, this is generated by 3 elements, x, y, and z, subject to the relations x to the a equals y to the b equals z to the c equals x, y, z is equal to 1. And so, okay, I gave you 3 generators, but the very last relation certainly expresses z in terms of x and y. So really this group is generated by 2 generators, x and y. So you should think of this as being generated by 2 elements, x and y. So that x has order a. That's not immediate from this. Maybe it has order divisor of a, but no, x actually has order a. Y has order b, and the product x, y, which okay is z inverse, it doesn't really matter, has order c. Okay, so it's a really kind of basic group. If you're trying, as we'll see in a second, if you're studying, for instance, finite groups that are generated by 2 elements, then this is a very natural group to consider. Okay. This group is also residually finite. What do I mean by that? The fastest way to say it is that it injects into its profinite completion. A more elementary way to say it is that it has many finite quotients, in the sense that if you give me any non-identity element of this group, then there's some homomorphism to a finite group under which your non-identity element does not go to the identity. Okay, so there are lots and lots of finite quotients of these groups. Okay, and so yeah, as I said, if G is any group generated by an element of order A and an element of order B, so that the product has order C, Well, kind of the whole point of this is that you get a homomorphism from this triangle group, surjective homomorphism onto G by sending little x to capital X and little y to capital Y. Okay, just as an aside, is this a strong condition on the finite group G in order to be a homomorphic image of one of these triangle groups? It certainly needs to be generated by two elements. So I think it kind of, whether you believe that most finite groups can be generated by two elements really depends on what kind of groups you're looking at. So it's pretty clear that C2 cross C2 cross C2, product of three cyclic groups, cannot be generated by two elements, nor can the Cartesian product of any three non-trivial groups be generated by two elements. On the other hand, if you're interested in non-commutative groups, it seems to become more likely. Every non-commutative finite simple group can be generated by two elements. That's an older result. I looked this up recently. So a recent result of King is that every finite simple group can be generated by two elements, where the first element has order 2 and the second element has prime order. Okay, and then by the way, even if you ask which finite simple groups can be generated by an element of order 2 together with an element of order 3, it's not all of them. A finite simple group doesn't have to have order a multiple of 3, but it's quite a lot of finite simple groups can be generated by an element of order 2 and an element of order 3. Okay. So now I want to introduce a small variant here. In fact, in my presentation, I want to allow A, B, and C to be equal to infinity, any or all of them to be equal to infinity. So what does that mean? Well, whenever you see a relation generator to the infinity equals 0, well, what does that mean? I have to tell you what that means. And I tell you that it means absolutely nothing. Okay, so that relation, if one of A, B, and C is equal to infinity, then you just remove that relation. It tells you nothing. And so, for instance, if you took if you took C to be equal to infinity, then you would be saying basically this group would be generated by an element X of order A, an element Y of order B, and an element Z that is totally unrestricted, except that it's equal to the inverse of X times Y. Okay, and so therefore you'd be getting the free product of the cyclic group of order A with the cyclic group of order B. So that's definitely relevant to modular things because
are the finite simple groups?
Hello, what?
A question. Yeah, are the finite simple groups generated by an element of order 2, an element of order 3? Are they known?
I think so. Yeah. I think there's a math overflow question about this.
Yeah, but now this paper of King, that result of King is said.
I'm having trouble hearing. I'm getting a lot of echoes on the questions.
So what?
Is it just me or other people hearing this? Okay.
No, there is a lot of echo. I think maybe there are two devices there, and that creates the echo. Maybe it can be shared on the chat, and I can ask.
Okay, that sounds like a good suggestion. Anyway, so yeah, there is information about. Okay. Yeah, so there is information about which finite simple groups can be generated by an element of order 2 and an element of order 3. Anyway, so right, so that's so in particular the 2-3 infinity triangle group. The 2-3 infinity triangle group is the modular group PSL2Z, and there's an element of order 2, and there's an element of order 3, so that's sort of well known and famous. And then in particular, if you took all of them to be equal to infinity, then you would be getting the free group on 2 generators, but you'd be getting a slightly exotic. You'd be getting a slightly exotic presentation of it because it would be given, it'd just be this XYZ subject to XYZ equals 1. And so you might think, in what topological context do you encounter that presentation of the free group on two generators, where it's actually free on two generators, but you're writing it as XYZ subject to the one relation that XYZ is equal to 1. Okay. Let me go on. So all I've done basically is define these triangle groups so far as abstract groups. What can you say about their structure, right? Just because you write down a group with generators and relations doesn't mean that it's easy or even possible to determine the structure of the group. These are very pleasant groups, actually. So it turns out that there's this natural invariant chi of A, B, and C, which is 1 over A plus 1 over B plus 1 over C minus 1, which is whether this invariant is positive, 0, or negative. So in other words, whether 1 over A plus 1 over B plus 1 over C is greater than 1, equal to 1, or less than 1 is telling us quite a lot about the structure of the group. So, and if you think about it, for most values of A, B, and C, it's the chi is going to be negative. Okay, so I'll call it triple spherical. If chi is greater than 0, it's no problem at all to write down a complete list of the spherical triples. So for any finite C, 2, 2C is a spherical triple. The group is the dihedral group of order 2C. You have 2, 3, 3, 2, 3, 4, 2, 3, 5. These give you the groups A4, S4, A5. So what do we take away from this? We take away from this that the spherical triangle groups are finite. And then if you look at this list of finite groups, you say, these are precisely the finite subgroups of PGL2 over the complex numbers, which is, of course, not a coincidence. Then you have the Euclidean triples, where the chi is equal to 0. And again, no problem to give a complete list. This first one is actually the infinite dihedral group, and then you have 3 more. And it's not so hard to show that these groups are infinite, unlike the spherical triples. They're not commutative, but they're extensions of one commutative group by another commutative group. So these are infinite solvable, not commutative groups. And the hyperbolic triples are the most interesting. This is everything else. These are groups that are infinite, and because they're residually finite, have lots of finite quotients. And then you say, all right, well, among all the hyperbolic triples, so these are the ones where chi is negative, how large can chi be, assuming that it's negative? That's a very easy exercise. You find that among all hyperbolic triples, the one with the largest, least negative chi is 237. Where chi turns out to be minus 1 over 42. And so we will call this 237 triangle group the Hurwitz group, which will come up later. This is one of the favorite triangle groups. Okay, so now I want to quickly go on to discuss the connection with geometry. So I would like to take a triangle with angles pi over A, pi over B, pi over C, and I would like to interpret these triangle groups as isometries involving the triangle. And you say to yourself, well, what do you mean a triangle with angles pi over A, pi over B, pi over C? Unless 1 over A plus 1 over B plus 1 over C is equal to 1, unless you're in the Euclidean case, you're not going to have such a triangle. And I will say, well, no, I didn't tell you where the triangle lives. If the angle sum is greater than pi, then you can get such a triangle on the Riemann sphere. If the angle sum is equal to pi, you get such a triangle in the Euclidean plane. If the angle sum is less than pi, you get such a triangle in the hyperbolic plane. Okay, if I allow sum of A, B, and C to be equal to infinity, I'm getting a triangle which has angle 0, which you can make sense of as well. If you have a hyperbolic triangle, that means it's an ideal triangle, some or all of whose vertices are on the boundary of the hyperbolic plane. But you can make sense of that. I don't want to worry about it right now. And so now I want to consider the isometry group generated by the reflections through the, so you get a line by extending the side of the triangle. I guess in the Riemann sphere case, the line is really a great circle on the Riemann sphere. But anyway, in all three of these cases, it makes sense to reflect through the sides of the triangle, okay? And so I can consider the subgroup of the isometry group of this corresponding plane generated by the sides of reflections through the sides of this three sides of the triangle. However, reflections or orientation reversing, I would like these, I would like to get groups of isometries that are complex analytic ultimately, and so therefore conformal, which should preserve oriented angles. And so I really don't want to have orientation reversing isometry, so I'm just going to take the index 2 subgroup of orientation preserving isometries, and that's easily done. That's going to be generated by the compositions of reflection in one side of the triangle followed by reflection in the next side of the triangle. So I call those delta A, delta B, delta C, all with bars over them. And if you think about it, if you compose reflections through these lines that meet at a certain angle, then the composition of those two reflections is going to be a rotation of twice the angle. So on the Euclidean plane, if I reflect through the x-axis and then I reflect through the y-axis, these two lines make an angle of pi/2. Overall, I get a rotation through pi. Okay, so it's pretty immediate to see that delta A to the A equals delta B to the B equals delta C to the C equals delta A, delta B, delta C equals 1. So in fact, this orientation preserving subgroup that we just defined is a homomorphic image of the triangle group. Okay, and so it turns out, in fact, that this homomorphism is injective. So I've kind of done the geometric group theory thing. I have an abstract group, and in order to study it, I faithfully realized it as a group of isometries of some nice geometric structure. So these hyperbolic, these triangle groups, excuse me, are all orientation preserving isometry groups of their respective planes, either the Riemann sphere, the complex plane, or the case of most interest to us, the hyperbolic plane. And in the last case, the group of orientation preserving isometries of the hyperbolic plane is PSL2R. Okay, so in particular, in that case, we're realizing the hyperbolic triangle group as a discrete subgroup of PSL2R, i.e. a Fuchsian group. Okay, and so now we can go on, we can say, you know, what happens if we take our plane and mod out by this triangle group? Well, the fundamental domain for the original discrete group that was generated by the reflections is the triangle. We're taking the index 2 subgroup, so the fundamental domain should double. You take the triangle and you reflect it through one of its sides. That's a fundamental domain. So this quadrilateral, this doubled triangle, is a fundamental domain of the triangle group. And you see that you have these edge identifications. And so if you identify the edges this way, this is pretty easy. There's some corner points, you know, so you can say orbifold if you like to say orbifold. But topologically, I'm certainly getting a Riemann sphere or a sphere by making this identification. So if I take my plane and I mod out by the triangle group, I'm going to get the projective line. Okay. Moreover, if I take my map from my entire plane to mapping out by the triangle group, then I can consider this map. Okay, in the case where it was a spherical triangle group, I'm really just mapping from, I have a finite map from P1 down to P1. That's much less interesting than what's happening in the other two cases. In the other two cases, my plane is non-compact and my quotient is compact. So I certainly have an infinite degree map. Okay, so this is an infinite degree branched covering, but it's not very branched. You can see from the picture that it's only going to be ramified at the vertices of this fundamental domain. And moreover, this top vertex is getting identified with this bottom vertex here. So there are only 3 ramification points downstairs. Okay, so the geometry of this entire infinite degree, except in the spherical case, cover is very nice. So in particular, any intermediate covering from this whole, from the non-compact plane down to the projective line, if the whole thing is only ramified over 3 points, then any intermediate covering will also only be ramified over 3 points. And this brings me to the key definition, or one of the most key definitions for the talk. So a Bailey map is going to be a finite degree branched cover. Here, X is a compact Riemann surface, okay? So, a finite degree branched cover to the projective line, which is only ramified over 3 points. So because the automorphism group of P1 acts triply transitively on P1, it doesn't really matter what the 3 points are. So just by composing with a linear fractional transformation, we might as well assume that the 3 points are 0, 1, and infinity, for instance. Okay, and so the point of this is that I just made this definition of Bailey maps, but then we immediately get a big source of Bailey maps from this modular interpretation. If I take any finite index subgroup of my triangle group, then just modding out my plane, again, it could be one of these three. I care about the hyperbolic plane the most. If I take my plane and I mod out by this finite index subgroup, and then I get a natural map to modding out by the entire triangle group. Well, this is this is the finite degree subcover of the usually infinite degree cover, and it's still ramified only over those 3 points. And so this is evidently a Bailey map where this is going, so X is going to be a compact Riemann surface, and the degree of this map is going to be the index of my finite index subgroup. Okay, so I get a lot of Bailey maps from finite index subgroups to the triangle group. And then this modular perspective also shows you that if you take a finite index normal subgroup of the triangle group, then you're going to get a Galois Bailey map just by the Galois theory of covers, right? Galois covers correspond to normal subgroups. Okay. So now there's some key topology, which I'm not going to discuss in detail. I hope you've seen it before. If you haven't, it's going to take me more than 5 minutes to explain it. So if I have a Galois Bailey map, so again, this is a branched cover from X to the projective line, branched over only 3 points, and it is a Galois cover. Okay, so the deck transformation group acts transitively on the fibers, and it has Galois group G. Well, because you have a Galois cover, the ramification indices are all going to be equal. What do I mean? Sorry, in the fiber over each one of the branch points, all the ramification indices are going to be equal. Why? Because it's a Galois cover, so the deck transformation group is acting transitively over the fibers. So whatever is happening over one point in the fiber is totally symmetric with what's happening over every other point in the fiber. So I can talk about a common ramification index for all the points over 0, I'll call that A. A common ramification index over 1, I'll call that B. A common ramification index over infinity, I'll call that C. And again, I can, by reordering 0, 1, and infinity, if I need to, I can assume that they come in increasing order. And now here comes the topological argument, the answer to what I was saying before. Where have you seen the presentation of a free group on 2 generators as XYZ such that XYZ equals 0? Well, that's a natural presentation for the fundamental group of the sphere minus 3 points. If you take any other point and you take these 3 loops, then these 3 loops, the homotopy classes of these loops are giving you the X, Y, and the Z in the fundamental group. And the one relation is that if you compose all 3 of these loops, then you can kind of run around the back of the Riemann sphere and collapse the path. So it's trivial. So again, by some more details involving choosing correct generators of the inertia groups, which have to be cyclic because we're doing ramification in characteristic 0, you will find that this Galois group G of the cover is the monodromy group of this branched cover, which becomes an unbranched cover when you remove the branched points. And so you will find that the Galois group is generated by the elements X, Y, Z, which are generators of the inertia groups at the points. and they will satisfy the correct relations that x to the a equals y to the b equals z to the c equals xyz equals 1. And so what's the point? The point is that if you have a Galois-Bailey map with Galois group G and ramification indices ABC, well, then that forces your group G to canonically be a homomorphic image of the ABC triangle group. Okay. You can also apply the Riemann-Hurwitz formula as you can to any branched cover. But again, it's much simpler if your branched cover is Galois, because again, all the ramification indices are going to be the same. So if you know the Riemann-Hurwitz formula, I promise you, if you apply it here, you'll get that the genus of the upstairs Riemann surface X is equal to 1 plus the order of the automorphism group, which is also the degree of the map, divided by 2 times 1 minus 1 over A minus 1 over B minus 1 over C. The negative of that is what I define chi to be. So the genus is 1 minus the order of the group divided by 2 times chi. So this has a nice upshot. We understand when we're doing spherical triples, Euclidean triples, or hyperbolic triples. So evidently, if the genus is 0 if and only if it's less than 1. So if and only if in this correction term here, we're subtracting something positive. So the genus is 0 if and only if we have a spherical triple. The genus is 1 if and only if this term goes away. So you have a Euclidean triple, and the genus is greater than or equal to 2 if and only if you have a hyperbolic triple. Okay, so again, for the most part, we're interested in hyperbolic triples. And so we know that we're going to have a hyperbolic triple if we have a Galois-Bailey map and the top Riemann surface has genus at least 2. Okay, and so if we combine this with the Riemann existence theorem, which is a result saying if you have a branched cover of Riemann surfaces and you pull out the branch points and then you get an unbranched cover on the non-compact Riemann surfaces, then sort of you can recover the entire branched cover as a holomorphic map from the topology of the unbranched cover. That's the sort of the moral of the Riemann existence theorem. Here, and conversely, from every unbranched cover, you can build your complex analytic map. So from that, it follows this conclusion that not only did we come up with a nice source of Galois-Bailey maps, every hyperbolic ABC Galois-Bailey map, equivalently every ABC Galois-Bailey map where the source curve has genus at least 2, is coming from a finite index normal subgroup of a hyperbolic triangle group. And again, here the A, B, and the C do all have to be finite because they're the ramification indices of this finite degree map. Okay, so this is really a very nice result. This is saying that there's a complete correspondence between Galois-Bailey maps and among Riemann surfaces of genus at least 2, there's a complete correspondence between Galois-Bailey maps and finite index normal subgroups of co-compact hyperbolic triangle groups. Okay. Maybe I'll come to a natural stopping point soon where I can ask if there are any questions. Let me just push this a little bit farther. So I just said that every Galois-Bailey map comes from this kind of modular perspective. Just using the Galois correspondence, you can extend that to all Bailey maps as long as the target has genus at least 2. Why? Because ironically, considering that one of the main themes of this talk is that Bailey maps are common, but Galois-Bailey maps are rare, that still seems to be true, despite the fact that if you start with any Bailey map, it's very easy to produce a Galois-Bailey map. You just take the Galois closure. Okay. Again, if you think of the correspondence between curves and function fields, I am literally taking the Galois closure of this finite degree field extension in characteristic 0. That's what I get. And again, just this number theory fact that compositum of extensions that are unramified away from something is going to be unramified. Unramified at a place of the base. The compositum of two extensions that are each unramified over some downstairs place will also be unramified over that downstairs place. So the Galois closure is going to be a Galois-Bailey map. Well, X has genus at least 2 and Y covers X, so Y certainly has genus at least 2. So by what I just said, there's this kind of uniformizing subgroup gamma sub Y, right? So that the Galois-Bailey map is obtained by modding out by gamma sub Y. But now by the Galois correspondence, gamma sub Y down to X is just going from H mod gamma Y to H modulo the triangle group. And this is something in between. So the something in between by Galois correspondence must correspond to an intermediate subgroup as well. So I guess what I'm saying here is that if I have Y down to X down to P1, then I can recognize the Y as the upper half plane modulo some gamma of Y. I know this is mapping down to the upper half plane modulo the triangle group. And so therefore in between, this must also correspond to modding out by some subgroup, which is larger than gamma. Okay, so the upshot of this is that at least in genus greater than or equal to 2, Bailey maps just correspond to finite index subgroups of hyperbolic triangle groups. Okay, and so this means that the whole thing of Bailey maps can be is being modularized, but it's also being discretized in the sense that you can do it in principle, you can do everything that you want just by looking at finite index subgroups of these discrete groups. Okay, so this is a natural pausing point. Does anybody have any questions at this point?
Perhaps I can ask a question, Peter. So in this business, one has to understand all finite index subgroups of the triangle group.
Mm-hmm.
And that is not something easy to understand, I presume.
It depends what you mean, but no. So somehow the point of the second talk is we will exhibit a family of particularly nice finite index subgroups of these triangle groups. But yeah, in general, I mean, you can sort of see what it is, like finding normal finite index subgroups of these triangle groups is more or less equivalent to understanding which finite groups can be generated by an element of order A and an element of order B so that the product has order C. And yeah, that's complicated.
Right. Good. And why is this very last line, at least in genus greater than or equal to 2? This is not the case in genus 0 and 1?
Well, I can't say hyperbolic in that case, right? So I'm going to give you some examples in genus 0 and 1. But so one thing that you would have to worry about is if your curve is genus 0 or 1, the Galois closure might still have, the Galois closure could have genus greater than or equal to 2. And so trying to figure out whether you're in the hyperbolic case or not is a little bit more complicated. So yeah, so in particular, if you decide that you only want to deal with hyperbolic triangle groups, then you should be in genus greater than or equal to 2. But I will show you examples coming up now in genus 0 and 1.
Good.
This is not true in case of the non-compact triangle groups.
Let me say it. The sense in which I didn't say non-compact works in our favor. So here I'm saying, maybe I'll come back. This will come back later. I'll say it later, but I'll just say, there's sort of two things going on. You can get a Bailey map from a non-compact triangle group and then you run the argument that I just gave you, and the upshot, okay, I guess I'll say it now. The upshot is going to be any Bailey map that you get from a non-compact triangle group, great, you got it, like X of P, you got from a non-compact triangle group. Because of the argument that I just made, you must also be able to get it from a compact triangle group. So the same curve can admit more than one uniformization, and that's a key part to what's happening. But yeah, okay, I will. You'll see that written down a little bit later. Okay, so those were good questions. Let me go on. I just want a little fact here, which in fact is going to be part of a theorem that I'll state later. But I think, oh right, so at the moment, this Galois-Bailey map seems to really it really seems to be a property of the map rather than the curve. So if I have a curve and I wonder whether it admits any Galois-Bailey map, then what do I need to do? I need to like range through all subgroups of the automorphism group of the curve. Let's assume the curve has genus at least 2, so the automorphism group is finite. So I range through all subgroups of the automorphism group and see if modding out by any of those subgroups gives me a Bailey map. That sounds hard. And so no, you don't have to do that. So here's the fact. If you have any Galois-Bailey map with source a curve of genus greater than or equal to 2, so since the genus is greater than or equal to 2, the entire automorphism group is finite. So you could just mod out by the entire automorphism group. And the fact is, that will also be a Bailey map. Okay, so what this means is that whether your curve admits a Galois-Bailey map is not really a property of how all groups act on your curve by automorphisms. It's much more directly a property of how the full automorphism group of the curve acts on it. Okay, we'll say a little bit more about this later. So in particular, though, this gives kind of this is really the key definition in the entire talk. So a curve over the complex numbers, excuse me, will be called a Galois-Bailey curve if it admits a Galois-Bailey map. And I just gave you this criterion for the necessary and sufficient criterion for that. But again, it's really a property of the curve itself. So some curves admit Galois-Bailey maps, some curves do not. I would like to understand this dichotomy. And in fact, there's a big theorem of Euclidean-Wolfart, which is explains the dichotomy. Let me, however, begin with some examples in low genus, okay? And so I should say that these examples are either to be found in my paper with John Voight, in which case they were definitely contributed by John, or they're found in a paper of Wolfart that is cited in our paper. Okay, so I'll start with genus 0.
Just to get it clarified, x by odd x is a quotient of P1.
I want the quotient to be P1, yeah.
No, I'm saying that x by odd x sits as a quotient of P1. So there is a mapping from x to P1.
Oh,
and
if
when
you have,
divide
yeah,
x
it would be a further quotient of P1. Yes, that's right. If you have a Bailey map, then you mod out, you go from modding out by a subgroup of the automorphism group to modding out by the full automorphism group.
Right.
So certainly this will be P1 if you have a Galois-Bailey map. Yeah. The rest of the exercises, you have to check that it's still only ramified over the 3 poles. Yeah. Okay. This is
good.
It's a fact. It's not the most profound thing in the world, but yeah. Right. If you have a Galois-Bailey map and then you further mod out, you still have a Galois-Bailey map. That's really what I'm saying. Okay, so let me go to my low genus example. So I'll start out in genus 0. So again, that's not the hyperbolic case, but we can still do it. So I do want like honest Bailey maps, by which I mean that it really is ramified over all 3 of those points. I won't go into full detail, but you're not excluding much. If you have a map over a map to P1 in characteristic 0, of course, as we are, if it were ramified at 0 points or 1 point, it would just have to be degree 1. So that's totally trivial. If it were ramified over 2 points, that's possible, but they're essentially all equivalent to t goes to t to the n. Okay, so if you're really not seeing very interesting maps if you require fewer than 3 ramification points. So I do want to require all 3 ramification points. And so here's an example. So again, if the genus is 0, the source Riemann surface is P1. So I'm just giving you a rational function on P1 so that the corresponding extension of function fields C of t over C of f of t is a Galois extension. That's what it means for this to be a Galois. And I want it to be a Bailey map, so I want it to only be ramified over 0, 1, and infinity. And so this degree 6 rational function is an S3 Galois Bailey map, and the ramification indices are 2, 2, and 3. Okay, so this is like the most spherical triple, basically, or well, close to it anyway. Right, and so in fact, for every spherical triple, there is because the spherical triples, as I said before, correspond to finite subgroups of PGL2, which after all is the automorphism group of the projective line. To every spherical triple, you are going to have a Galois Bailey map from P1 to P1 with that group as an automorphism group. Okay, so this is an example of a Galois Bailey map in genus 0. Now I want to talk about Galois Bailey maps in genus 1, and then I want to talk more importantly about Galois Bailey maps in genus greater than or equal to 2. Okay, so in genus 1, it's at least over the complex numbers, it's an elliptic curve. So this is exceptional because the automorphism group of an elliptic curve, strictly speaking, is infinite because you can translate by all the points of the elliptic curve. So maybe it's better to fix a base point of your elliptic curve and only consider automorphisms that fix that marked point, and that almost rigidifies the situation. So now the automorphism group is finite, as is well known in elliptic curve theory. The automorphism group of the curve that fixed the point always includes plus or minus 1, and is almost always just equal to plus or minus 1. There's only 2 elliptic curves, my least favorite elliptic curves at this point in my life, that are the exceptions. If j equals 1728, like the uniformizing lattice is the Gaussian integers, that's a uniformizing lattice. So you have the 4th roots of I acts as an automorphism fixing the origin. If you mod out by the cyclic mu4 action, then that is a Galois Bailey map. The group, well, it's mu4 is the same as C4, so that's a 2, 4, 4 Galois Bailey map. That's a Euclidean triple, 1/2 plus 1/4 plus 1/4 equals 1. Or you could take j equals 0, in which case a uniformizing lattice would be the ring of integers in Q adjoint square root minus 3. And so naturally the 6th roots of unity are going to act on it. And then the elliptic curve modulo that automorphism group is again a Galois Bailey map with ramification 2, 3, 6. And so by a small result in the paper with John, in fact, there are a few more Galois Bailey maps from elliptic curves. You could also get 3, 3, 3 from an elliptic curve with j invariant 0. But if you have an elliptic curve that admits a Galois Bailey map, then the j invariant has to be 0 or 1728. And so this I think is helpful in understanding what the class of curves admitting Galois Bailey maps are. This is such a familiar case, but among all elliptic curves over the complex numbers, 2 of them have more automorphisms than all the rest. It's these 2, and these are the ones that are special in terms of admitting Galois Bailey maps. Okay. Now I want to move on to, following a paper of Wolfart, I want to move on to genus 2, genus 3, genus 4, mostly genus 2 and 3. So in genus 2, it turns out there are exactly 3 curves that admit Galois Bailey maps. They have to be all curves in genus 2 are hyperelliptic. So really, if you're trying to, you should try to write down a hyperelliptic curve that has a lot of automorphisms, is kind of the idea. And so this is y squared equals x to the 6th minus x. This, by the way, is kind of a generalization of this one. This elliptic curve has an equation y squared equals x cubed minus x. And this one has an equation y squared equals x cubed minus 1. So this genus 2 curve with defining polynomial x to the 6 equals x is kind of a genus 2 analog of this genus 1 curve. And this genus 2 curve with defining polynomial x to the 6 minus 1 is kind of a genus 2 analog of this genus 1 curve. Okay. And so yeah, you see that the groups are. I've told you what the groups are. The most interesting one maybe is GL2F3. These are all solvable groups. Okay, so they're exactly 3 genus 2 curves that admit Galois-Bailey maps. Okay, here when I'm giving you the indices, this is for the sort of the canonical Galois-Bailey map where you mod out by the entire automorphism group, and therefore this group is the full automorphism group of these curves. All right. Now we go on to genus 3, which is much more interesting. So in genus 3, there are precisely 8 curves that admit Galois-Bailey maps, and we'll talk about what happens when you mod out by their automorphism group. 4 of them are hyperelliptic, and you see again some of these analogs. You see this x to the 8 minus x. That's again an analog of the other 2 curves. You see the x to the 8 minus 1. That's an analog of the other 2 curves. There's maybe this last hyperelliptic curve is a little harder to explain where it's coming from. Then you get 4 non-hyperelliptic genus 3 curves admitting Galois-Bailey maps. There's some interesting sort of trigonal one here, and then here there's a maybe this is like a Picard curve or something. Anyway, so there's a couple of them that are just they do come equipped with cyclic maps down to the projected line sort of easily. Okay, the 2 most interesting curves on this list are this guy, which is the Fermat quartic. Okay, x to the 4th plus y to the 4th equals 1. You can sort of see the automorphisms here. The C4 is coming from adjusting x by a 4th root of unity. The second C4 is coming from adjusting y by a 4th root of unity. Why am I semi-direct producting with S3 or Reith producting or whatever you want to say? Well, because if I took the projective equation, x to the 4th plus y to the 4th equals z to the 4th, then you could obviously S3 permute all the variables. And so the automorphism group of the Fermat curve is kind of obviously has this, the Fermat curve x to the n plus y to the n equals z to the n kind of obviously has a Cn cross Cn semi-direct product S3 automorphism group on it, and that makes it a Bailey map. This is also a generalization of an elliptic curve because the elliptic curve with j equals 0 is also the Fermat cubic. Okay, so there's some special curves which are related to other special curves. It is an exercise that every Fermat curve with x to the n plus y to the n equals 1 for n greater than or equal to 3 is a Galois-Bailey curve. So the Fermat curves, being a nice family of curves, they're also nice in this sense as well. And then maybe the most interesting curve is this Klein quartic given by this equation, which certainly shows a threefold symmetry. So this Klein quartic, the automorphism group is PSL2F7. Wow, that's a pretty cool automorphism group for a curve of genus 3. It has size 168. It is the largest of these groups, so it's certainly the largest automorphism group of any curve in genus 3. And in fact, this Klein quartic is x of 7. Okay, so this is among the modular curves x of p. They have genus 0 for p equals 2, 3, and 5. So maybe forget about them. And so this is the first modular curve x of p, which has genus greater than or equal to 2. And yeah, so this is appearing in our family of maps. Okay, and so there are more curves in genus 4, but actually they're kind of less interesting than in genus 3. There are 11 of them. 4 of them are hyperelliptic. 7 of them are not. The largest automorphism group of a Galois-Bailey curve in genus 4 is S5. Okay, non-solvable group. It's interesting, but notice that S5 is order 120, which is smaller than the order of PSL2 F7. So nobody said that as you step up the genera of your curve, the size of the largest possible automorphism group, it doesn't have to increase. Okay, so there are some genera where you have really large automorphism groups, even compared to some larger genera. Okay, so now we come to this is really the last this is the last main result of the talk, and then for the remainder, hopefully only 5 or 10 minutes after this, I'll talk about a couple of consequences of this talk. So this is a theorem of Wolfart in one of his papers, which is cited in my paper with John. So these are equivalent conditions on a curve to be a curve of genus at least 2 to be a Galois-Bailey curve. So we saw I already mentioned the second one already. So let's move on to the third one. It's pretty similar to what I said before. I proved most of this. That every Galois-Bailey curve is kind of uniformized is the upper half plane modulo a finite index normal subgroup of a co-compact triangle group. So again, here I'm emphasizing that the C here is less than infinity. So maybe you can uniformize it by a non-co-compact triangle group, but if you can also uniformize it by a co-compact triangle group. But the extra condition here is that the group is torsion-free, so has no elements of finite order. So, okay, if I have a Fuchsian group and it's co-compact, it can't have any cusps, it's torsion-free, it can't have any elliptic points. So this is a Fuchsian group of hyperbolic type. All of its elements have to be hyperbolic. In particular, that means that the uniformization map from the upper half plane down to X is, well, first of all, I don't need to compactify it by putting the bar above. I didn't make a big deal about that before, but that's what the bar over the H. If you have cusps, then you need to compactify. I don't have cusps, so I don't need to compactify. I don't have any elliptic elements, so I don't have any ramification either. Therefore, the map from H down to H mod gamma is literally an unramified cover. Therefore, gamma is the fundamental group of X. Okay, really, it is the uniformation map and the uniformization map in the strongest sense. Every curve of genus at least 2 its universal cover is going to be the hyperbolic plane. You mod out by the group of deck transformations, which is of course the fundamental group. So yeah, so every Galois-Bailey map admits its canonical uniformization map. It's the one where the group is the fundamental group, being a normal finite index torsion-free subgroup of a hyperbolic triangle group. And then the last one is really interesting too. So if you look at the moduli space of genus G curves, I'm going to view this as a complex analytic space. The point being, I want the usual analytic topology on this thing. I don't want the Zariski topology. I'm going to look at the function that assigns to a point on the moduli space, so the isomorphism class of a genus G curve, the size of its automorphism group. And the result here is that the Galois-Bailey maps are precisely the ones on which this function attains a strict local maximum at that point. What does that mean? It means that you have some little ball around your point in the moduli space, so that at this exact center of the ball, which is your point, you have strictly more automorphisms than you have at any nearby point. Okay, so we really saw this. I'm cheating a little bit because this is genus greater than or equal to 2, but we really saw the analogous phenomenon in genus 1. In genus 1, the moduli space is just the affine line, and if you take the automorphisms which fix the origin, then the size of the automorphism group at every point on the affine line except for 2 points was equal to 2. At this point, the size of the automorphism group discontinuously jumps up to 4. At this point, the size of the automorphism group discontinuously jumps up to 6. And so that's a very interesting and somewhat subtle extremal property of these Galois-Bailey curves that basically it means that along with their automorphism group does not deform in families. So this is an automorphism group that can only be attained by a zero-dimensional loci inside the modular space. Okay. So I'll quickly discuss some consequences. Again, to bring back the point that I was asked about before, if you look at the modular curves X of P, they're given to us as this sort of weaker uniformization by a subgroup of a non-co-compact triangle group, gamma of P, subgroup of the modular group. It follows, I actually gave the proof of that part, it follows that they can also be uniformized by a subgroup of this compact triangle group. Okay, so the same curve can have multiple uniformizations. And again, this group is really special because it's 2, 3, 7. So by definition, a Hurwitz curve is going to be a 2, 3, 7 Galois-Bailey curve. Okay, so Hurwitz curves are going to attain the Hurwitz bound 84G-1. And so this is the PSL2F7 is the smallest non-trivial finite quotient of the 2, 3, 7 triangle group. So it's pretty interesting. And so therefore this Klein-Quartic is the smallest Hurwitz curve. Okay. In the second lecture, we'll see that it's also a Shimura curve.
Condition 4.
Yep.
Condition 4 in the theorem, does that just mean that in the modular space, the curve is an isolated point?
Well, what do you mean?
Isolated point that, yeah, for
I mean, the moduli space is connected. Any two curves in the same genus can be deformed to each other.
Yeah, it's connected, but with anything less than the automorphism group, but still larger automorphism group. So that moduli of that is at least one-dimensional or something.
Say again. Sorry. So if you do what?
So if you take a group proper subgroup of Artex, and if you consider the curves which have that that as a automorphism group, so that that space is some that's not an isolated point. That's some something.
I mean, I think what you're again, I think that for any given group that occurs as the automorphism group of a curve of genus G, you can look at the locus in the moduli space of curves that attain that group. And so, yeah, these are the ones where the locus of curves that have, at least that automorphism group are isolated. So yeah, I mean, the loci that have that automorphism group is zero-dimensional. So that maybe that's the. Is that answering what you're asking?
Yeah, I think so. In the moduli space, these are the all these are the singular point is in the singular locus.
Oh, that's also true. Yeah. So in genus, in genus locus, maybe at least 4. I believe these are precisely the isolated singularities of the moduli space. Yes, that's what you're asking.
In the singular locus, these are really isolated points.
Yes, that is also true. Yeah, so if the genus is large enough, I can't remember, I think 4 is large enough, maybe 3 is large enough. Yes, and there's lots of another characterization is they are precisely the isolated singularities. That's right. Okay, I want to finish soon, and I think I will. Yeah, this last example, I realize I should talk to John about it. I think there's a deduction that isn't quite warranted here, but maybe I'm not understanding something correctly. I wanted to deduce the Hurwitz bound from this result. And so I do the calculation. So if you can assume that the absolute maximum of the size of the automorphism group comes from a Galois-Bailey curve, then sure, you do this easy Riemann-Hurwitz argument, and you see that this is the formula for the size of the automorphism group. And certainly, as we said, this minus chi is at least 1/42, so you maximize it by taking it to be, taking ABC to be 237. And so yeah, if you will grant me that the absolute maximum comes from a Galois-Bailey curve, then you deduce the Hurwitz bound from this. And you see that equality occurs if and only if you have a Galois-Bailey Hurwitz curve, 237 curve. But actually, I wonder if maybe this was my mistake when we were writing the paper. So I do say strict local maximum here. So this is kind of related to what we were talking about before. For this to be true, you need to believe that the absolute maximum occurs at an isolated point and not on some higher dimensional locus within the automorphism group. And I strongly believe that to be true, but I don't think it's a direct consequence of what was being said here. Yeah. Anyway, but so certainly this result is closely related to the Hurwitz bound. Hurwitz curves are a subclass. They are precisely the 237 Galois-Bailey curves, and they're the ones that have automorphism group, the largest possible one relative to the genus. But kind of any ABC Galois-Bailey curve will give you a similar formula for the size of the automorphism group in terms of the genus. You see that right here. It's just going to be something smaller than 84. Okay, and so let me move on, and again, this is my last page for this first talk, so I'm almost done. So again, speaking of Hurwitz curves, again, because the Hurwitz group is residually finite, it has it has arbitrarily large finite quotients. Also, it's in the second talk, it's an arithmetic group, so we would explicitly define lots of congruent subgroups, and so you'll get it that way. But sure. All of these triangle groups have infinitely many, hyperbolic triangle groups have arbitrarily large finite quotients. So therefore, you're going to get Hurwitz curves of arbitrarily large genera, but not all genera, as is well known. And in fact, we already saw that. If you go back to our classification, we did not have a curve whose automorphism group has size 84 times g minus 1. We didn't have that in genus 2. It would have to have size 84. But all these things are smaller. We didn't have it in genus 4. The largest size was 120, which is much less than 84 times 3. And so yeah, the Hurwitz curves are maximal in a very strong sense with respect to how large they are compared to g minus 1. They certainly don't occur in all genera. The next genus in which you have a Hurwitz curve is g equals 7. This is another very famous curve, the Fricka-McBeath curve. On the other hand, Galois-Bailey curves do exist in all genera, and the pattern that we thought that we found persists. So you could always take the hyperelliptic curve y squared equals x to the 2g plus 1 minus 1. I think you can also always take y squared equals x to the 2g plus 1 minus x. And so it's a nice, I think it's an interesting exercise to check that this, find the automorphism group and check that you get a Bailey map. And I found a paper on the archive, a preprint from a few years ago by Muller and Pink, where they completely classify all hyperelliptic Galois-Bailey curves, which seems very nice. And so in particular, these curves appear in their families. And so, yeah, what do I want to end with? I want to end with the observation that we saw in the data or the examples before. For each genus, there are only finitely many Galois-Bailey curves of genus G. Why is that? Well, for fixed G, there's only finitely many possible automorphism groups. We kind of took that as input, so that's a well-known fact. And so then we have this relation. If you can assume the genus and the size of the automorphism group is fixed, and then the Riemann-Hurwitz formula gives you this, and it's very elementary to see that whatever rational number I put on the right-hand side here, there's only going to be finitely many A, B, and C that satisfy it. And so what does that mean? That means that going back to our uniformizations, that means that we'll only have finitely many triples A, B, and C that could possibly work for a fixed genus. And because we know that the size of the automorphism group, which is the index of the normal subgroup, is fixed, well, now I have finitely many finitely generated groups, and I'm ranging over all subgroups of a given finite index. Well, just by reducing to the case of free groups, a finitely generated group has only finitely many subgroups of any fixed index. And so already we proved there are only finitely many. Okay, so again, I mean, as was kind of implicit maybe in the examples that I gave. So yeah, so this is a very, very special family of curves. For every genus G greater than or equal to 2, the Galois-Bailey curves are a non-empty finite sublocus of the moduli space of curves. Again, they're precisely the zero-dimensional subloci in terms of the automorphism group. So in some sense, as far as the automorphism group is concerned, these are precisely the most special curves and are very interesting to study. There's a little bit of a paradox here because, well, by this important theorem of Bailey, every curve over Q bar admits a Bailey map. So of course there are infinitely many curves of every genus that admit a Bailey map. So why are there so many curves that admit a Bailey map and so few curves that admit a Galois Bailey map? Because if you can just take the Galois closure, so if you revisit this argument even without a Galois Bailey map, you will realize that while every curve of fixed genus admits over Q bar, admits a Bailey map, the degrees of these Bailey maps are going to go up and up and up and up. And so now if I take a Bailey map of a very large degree and then I take its Galois closure, well, the degree only got larger, and then that degree is the size of the Galois group. And so therefore I'm getting Galois Bailey maps where the automorphism group is extremely large. Therefore the genus is extremely large. And so yeah, the paradox is, despite the fact that there are Bailey maps all over the damn place, Galois Bailey maps are excruciatingly rare. So for any fixed genus, there are only finitely many, but some curves of genus G that admit a Galois Bailey map, and they're very interesting to study. In the next talk, I will focus in on the case where the group is PSL2 or PGL2 over finite fields. And I will stop there. Thank you.
Good. Do we take some questions now? I mean, indeed, if there are some questions, it's good to get them clarified now.
I want to get one thing clarified. Can I ask?
Sure.
Please go ahead and ask.
Yeah, for a given genus, there are only finitely many groups, finitely many finite groups which can act on the surface of a given genus.
Faithfully, sure, yeah. Mhm.
Yeah, so in the moduli space, the curves admitting any non-trivial finite group is is in the singular set.
Right? Is what?
And so among them, you say that you are saying that the Bailey maps are only finitely many. Yeah.
I'm saying that the curves that admit a Galois Bailey map are finitely many.
And so the corresponding groups are very special.
That is also true. But of course, the finiteness statement for the curves is much stronger than just the finiteness statement for the groups.
Yeah, there is a program for computing groups, finite groups, which can act on a given genus. So,
right, but you see what I'm saying, right? Just because you know what the group is. I mean, of course, there are certain. We're looking at the zero-dimensional loci inside the moduli space of curves, but I mean, for any G, you have the hyperelliptic locus where Z mod 2 acts on it. So yeah, just because you fix the group doesn't. You still get to ask what are the curves for what, okay, that the group G can act faithfully on some curve of genus G. Then you ask, well, for which curves of genus G can that group G act faithfully? And in this case, well, I guess I'm not saying it's interesting. What I'm not directly saying is, well, so it could be true, maybe that the same group occurs as the Galois group of a Bailey map, but then maybe it acts in a different way, so that the quotient is not a Bailey map, and then there's like a positive dimensional subloci of curves that have that group. That begins to get interesting. I don't actually know whether or not that occurs, but it is allowed to occur by what I said. I mean, one question I realized when I asked this, so there are various synonyms for these curves. One of them is they're called Riemann surfaces with many automorphisms. That's one of Euclidean Wolfart's terminologies. And just while I was giving a trial run of the talk this morning, I asked myself, okay, if that's true, if you have one of these curves that has, a Galois-Bailey curve, it has a certain automorphism group, then you take a different curve of the same genus that has a strictly larger automorphism group. Well, if the first curve had many automorphisms and the second curve has more automorphisms, does the second curve have to be a Galois-Bailey curve as well? And I don't know, actually. So that's also, it's the condition on what the automorphism group has to be in order to be a Galois-Bailey curve is not strictly a numerical condition, as we saw. So I actually think that's a very interesting question. By the way, it's very likely that somebody else knows the answer to this question. I don't seriously think about modular curves with automorphisms. But yeah, as far as I know, it could be the case. I would be very interested if someone knows the answer either way. I'd be very interested. So could you have a Galois-Bailey curve of genus G? Then you have another curve of genus G that has a larger automorphism group, but when you mod out by that automorphism group, you do not get a Bailey.